Okay, so we are going to pick up where we left off last class. And before we even start moving forward, I actually would like to chat about where we've been. Okay, at the beginning of our note packet last class, we started to talk about position and more specifically displacement. Okay, and the grand things that we need to know in terms of displacement, which is very important information. Then we went ahead and we started to do something that seemed like it was totally different in the fact that it was a position versus time graph. We found that on those position versus time graphs that if we go ahead and find the slope on our data, then it will tell us something very meaningful. What was that very meaningful thing that we found on the slopes of those graphs? And I will give you a hint in case those of you don't remember. It's in nice blue font, it's large print, and it has a line underneath it on the board.
Average velocity.
We found, thank you, average velocity on those graphs. Now we're going to formally put it together along with some other things today. Okay? So we have seen from what we did last class that calculating the slope line position versus time graph gives us something very specific. Okay? It gives us that average velocity, and it gives it to us in our appropriate units in meters per second. Okay? So average velocity is our second major concept that we're kind of talking about here. And since we're starting with horizontal motion, you will see on occasion the notation of Vx. The x as a subscript is a friendly reminder at this point that we are talking about a velocity along the x-axis. Okay? So we're not dealing with anything on a vertical axis just yet. And that's what that x notation is going to tell us. The bar over top is just simply mathematical notation for average, as we just talked about with our formative today. Okay? So to find Vx, okay, a couple of ways we can find it. If we know our displacement and we know a duration of time, we can calculate it that way. Or we can find it as a slope on a position versus time graph. As we did state, the SI units are going to be in meters per second, which means that if we have a measurement of displacement, it must be done in meters. If it's not done in meters, we'll have the conversion so that it will be expressed in meters. And our value of time will need to be expressed in seconds. Now, on the two graphs that we did last class, the sample graph and the chicken graph you did for today, they were all linear graphs. Okay? Our data points were all connected by straight lines. It was going to be pretty easy to go ahead and say, even if they weren't consecutive data points, we still could find the average between them. We are not limited to linear graphs in terms of finding average velocity. We can do that on exponential graphs too. Okay? So we can find the average velocity on a position versus time graph simply by drawing a line between any 2 points on any position versus time graph, exponential or linear. So let's take a look at points A and B on the graph that's on the board and on your notes. Could we calculate, if we knew the exact position values, could we calculate the average velocity between points A and B? Yes. We would calculate it. Would it be a positive average? Would it be a negative average? Would it be zero? We should expect it to be positive. Why? It's a positive slope. That's what the slope would tell us. That between those 2 points, we would have a positive average velocity. What about A and F? Assuming that we knew those points, what kind of average should we expect? It would be a negative average velocity. It wasn't necessarily perfectly drawn, but if it were point A, and let's call it point blue, which is, let's call it directly opposite that, what would the average be between point A and point blue? It would be an average of 0. I will ask you a trick question. I believe I may have asked you last class. If the average is 0, is it possible for that object to still move? Absolutely. Okay. So we can go ahead and make sure that when we're taking a look at these things, that it's not necessarily the average tells us everything that's going on. It just tells us a quick snapshot of what we're dealing with. So from point A to point blue, certainly the data tells us the object is moving. It just happens to be that between those 2 points, that it's actually going to be an average of 0. So effectively, all you need to do is, if we're trying to do a quick check, positive, negative, or 0, just look at the slope. Positive slope tells us it would be a positive average velocity. negative slope would be a negative average velocity. Zero slope, or even if it's very close to a zero slope, then we should be getting numerical values that should be pretty close to a zero at that point. Okay, so very quickly, let's just take a quick check-in at our chicken graphs. Okay, certainly we should have the label of where we are. Okay, we have our title, position versus time, our x-axis label of time and units of seconds. Okay, our y-axis position expressed in meters. Okay, you could have a little bit different numbering than what's on the board, but it, for the most part, needs to be spread out. Okay, and I don't think for most people the x-axis is the issue, it's the y-axis. Did we make sure that we spread that out when we're having 8 meters relatively close to the top of our page, or the top of the graph? If it is, awesome, okay, because that's where it should be. Okay? And then we will go ahead to the last part, which I have here in PDF for us. Even though it looks a little different than how it is on your page, please check your average velocity calculation. The exact same process as to what we just did for our formative today, but those should be the velocity values, the average velocity values that we got. Okay, just give a second just to do quick checks. So just to recap, again, we could take a look at any position versus time graph, any 2 data points on there, and we can figure out what the average velocity would be for that duration of time. Are we good with checking this? Okay. So then coming to the next step. Okay, so that's great when we have an average velocity. I think we kind of can sum that up pretty well from what we did from the last class. But there are going to be instances when average velocity is not going to be all that helpful. Just I want you to stop for a second. Don't worry about the notes. I want you to envision something for a second. Okay? So let's imagine that you are driving home from school today, and you just happen to be exceeding the legal speed limit on your way home. Officer is going to come up to your window and probably have a little chat with you. You know that you were speeding. I would love for you to try this. See how it works. Well, officer, I know at the moment that I passed you, I was going 25 miles an hour over the speed limit, but I was sitting at that stop sign for the previous 5 minutes. So if you take my average velocity over the last 7 minutes, you'd actually find that it would be lower than what the legal speed limit would be. Do you think that the officer would be very understanding to your explanation of average velocity? Of course he will. Depends on the route. What will probably happen is, that's nice, here's your ticket. Okay? So there are going to be instances when average velocity probably isn't going to help you out. Okay? We might need to know instantaneous velocity, or a velocity at a given moment. And how we do that is same general principle, but we just need to frame things a little bit differently. Okay? So in physics land, we do need to be able to specify our velocity just as precisely as we did with our position. And in order to do that mathematically, we need a little bit different tool in our tool shed. Okay? We need to be able to use calculus. Now, at first when you hear that term, some of you, your heart rate starts to elevate very quickly. For some of you, you start to stress out. I promise you, it is easy. Just work with me, okay? And we'll do that today. We're going to do some calculus today, okay? And we're going to do this in physics by taking smaller and smaller intervals of time on our position versus time graph. So now, let's get to the notes, okay? In terms of what we see, let's say we took that same position versus time graph we were just talking about earlier, and we wanted to find the instantaneous velocity at point A. Well, on our graph, between points A and B, that was 10 seconds apart. And if we took the average velocity from 0 to 10 seconds, it gives us a general idea of maybe what was happening during that 10-second interval. But what would happen if we took that from 10 seconds to 5 seconds? Would that give us a better idea as to what our instantaneous velocity would be? It'd be a little bit better. What if we shrunk that from 5 seconds to 1 second? Would that give us a better depiction of what it is that we're doing? What if we took it from 1 second down to 1,000th of a second? Then we're starting to get a lot closer to getting an exact value for a given moment in time. So all we're going to do is we're going to take the concept of average velocity and just apply it to effectively a very short period of time. So short that effectively it will be the same time. Now, there are many ways in which we can do this in practicality, but this is technically the definition of instantaneous velocity. It is the limiting value of the ratio of delta x over delta t as delta t approaches 0. Okay? That's what the textbook definition is. But really, it's just the limit of the average velocity as the time approaches 0. We're going to make smaller and smaller time intervals until we can do this. We can interpret the instantaneous velocity. Notice there's no ball. Instantaneous velocity graphically by drawing a tangent line at that point on our data set and finding its slope. Now, those of you who don't know what a tangent line is, or don't know what slope is, or don't know what a graph is, but that's what we'll do. We're going to draw a tangent line, and we'll be able to find the slope. So, continuing on, it's still the same stuff from the previous page. We just want to make sure it was there. And lastly, we don't want to have to say instantaneous velocity every time we're talking about instantaneous velocity. It is a mouthful to say. So from here on out, we will simply just say velocity. So if we're talking about what is the velocity here, we're talking about a velocity at that instant, at that given moment. Okay? If we're then going to talk about an average velocity, we'll call it average velocity. But otherwise, velocity is instantaneous velocity from here on out. Okay, so let's go ahead and put this to practice. Okay, so here we go. Simple problem. An object moved along the x-axis as shown in the position versus time graph to the right. We're going to determine the object displacement from 1 to 3 seconds and from 4 to 6 seconds. Then we're going to find the average velocity during those two time intervals. And then we're going to find the object's instantaneous velocity at 2 seconds and at 6 seconds. Don't worry about the calculus extension at the bottom, even though it's important. Leave some space down there, but we'll solve everything else out to the side. Okay, so here we go. Let's figure out the object's displacement from 1 to 3 seconds. Well, that means we have to read the graph because we don't have a data table. So at 1 second, what is our position? 11. Thank you for reading that properly when we trace that up. At 3 seconds, we trace it up, and that would be 3. So we're going, think about this from a number line. We're going from 11 to 3. Are we going to the left or to the right? We're going to the left. Even though we're still all the way to the right of the origin, we're starting at 11, and we're going all the way until we get to 3. So we're expecting a negative displacement, correct? All right. And then what is your final position? 3. What is your initial position? 11. So what would be final minus initial? 3 minus 11 would give you, it would be for part A of this, we'll just say that would be the negative 8 meters. And then what about from 4 to 6 seconds on our graph? At 4, our position is 2. At 6, our position is 5. At 6, we trace it across, it would get a position of 5. So 5 minus 2 would give us 3 meters for that second interval. And I know I'm kind of talking you through this. We can, of course, write it out and do that. But I'm just doing this as a quick glance look at that, just so we can figure out. Slopes also tell us what direction we're traveling. Okay, so now we're going to do part B. So I'm going to do part B over here. We're going to calculate the average velocity during these two time intervals. Okay, so that means V bar, and it's going to mean x final minus x initial over t final minus t initial. Now, from 1 to 3 seconds, that's very easy. From 1 to 3 seconds. By the way, when you plug in values for a delta t or a t final minus t initial, it should always give you a positive result. If you legitimately get a negative value for a delta t or a t final minus t initial, and you can prove it, you let me know. We'll go into business and we'll make billions of dollars. Until we figure out how to go back in time, though, we need to make sure that we are progressing forward with time. So our time value should always be positive. Okay. Now, as we did with our previous graph, come back and check it. What is our position at a time of 3 seconds? Okay, we look it up. That would have been 3. Then at 1 second, we just chatted about these points. That would be 11. So that would be our negative 8 meters over 2 seconds. That would give us negative 4 meters per second. So our average over that range from 1 to 3 seconds would have been negative 4 meters per second. Okay? Now, same deal. X final minus x initial over t final minus t initial. Okay? Now we're going to go from 4 to 6 seconds. Okay? Well, at 4 seconds, we said it was a position of 2. Then at 6 seconds, we said that was a position of 5. Well, 5 minus 2 would give us 3. 3 divided by 2 would give us 1.5 meters per second. Would be the average velocity during that interval. Okay. Now those two averages, that's nice. But if this is going back to our police officer pulling us over example, is that really going to be helpful? And for a duration of 2 seconds. Things can change a lot in 2 seconds. Okay? I'm going to erase this. Is that okay? Does everyone have this down so far? I need space to do part C. So then for part C, find the object's instantaneous velocity at a time of 2 seconds and at 6 seconds. If you actually look very carefully at your graph, and it doesn't copy all that well, but it's there already is a tangent line that is drawn in. What is a tangent line? It is a line that only touches the curve at that point. Does it cross over our data? No. It should never cross over the curve. It only just barely touches at that point. And fortunately for us, at least in terms of 2 seconds, it's already drawn for us here. So we have some options as to how we find the slope of this line. I will always suggest one of your data points needs to be the point at which this is tangent to. Okay, so being as we're going to do this first for 2 seconds, one of the 2 data points that we're going to use on our tangent line has to be the point it's tangent to. The other point, we need to do our best job selecting a point where we at least can comfortably state it gets very close to intersecting the grid. And I happen to know the function and I know this tangent line. There are 2 points on this graph that we know it will intersect. What do you think are those 2 points? At what time value? Okay? Actually, at 3, it doesn't. It's very close, but it doesn't. But at 3.5, it does. Okay, so over here, this would be one point that we could choose. It'll be the point that I end up using for this, but there is one other one, should you be adventurous. What do you think it is? It's at a time of 0. Okay. Now, you will only use 2 of these data points, and one of them will be the point it is tangent to. Why? Because when you hand draw these, which you will do later today, it's going to be harder to get an exact value. And that's at least usually one very clearly defined point that we can work with. Alright, so before we even really dive into finding the slope, what do we treat as final and initial? And now we can just kind of have these random points. Whatever points you choose, you will always work from left to right. leftmost point that you choose will be your initial. The rightmost point will be your final. Why? Time is always progressing as you go to the right. So, for the instantaneous velocity at 2 seconds, we're still going to do x final minus x initial over t final minus t initial. But we're just going to actually use the data points that we have here. And for me, I'm going to use this point at 2 seconds and this point at 3.5 seconds. So 3.5 minus 2. At 2 seconds, we know that that is a position of 6. What is the position on this tangent line at 3.5 seconds? 0. Okay? So 0 minus 6, negative 6. 3.5 minus 2, 1.5. What is negative 6 divided by 1.5? Negative 4, and it is a velocity of meters per second. Now, it just happens to be that the average velocity from, 1 to 3 seconds is the same value as what the instantaneous is at 2 seconds. It just happens to be a coincidence. It's actually more than likely never going to work out that way. Just the way it is. So how would we do this at 6 seconds? Do we have a generated tangent line that's already drawn for us? No. So we would have to draw our own. And I'm actually going to kind of skip this a little bit because we're going to do it what we'll do down below. But we would have to look, okay, here is the data point on our curve at a time of 6 seconds. Using your ruler and very, very precise movements, we will try to draw a tangent line that is only going to touch the curve at that point. And I actually still didn't even do the best job hand drawing because I don't have a ruler to do this right now. You with your rulers, though, you should be able to draw that a little bit better. Now, am I going to expect some variance in your answers with a hand-drawn tangent line? Absolutely. Because I know that none of you are going to draw the same tangent line. But just try your best to make sure that it's looking like that line would only intersect at that point. Or another way to think about it, kind of, look at the amount of spacing you have on one side and on the other side. It probably should be relatively close. And at least that way it's going to give you a pretty good guesstimate as to what that would be. Any questions with what we've done so far? Yes? No? Maybe? Good. Now let's go down to the calc extension. Just curious, by show of hands, how many of you are either in or have taken AB Calc or BC? Okay, good. Okay. Now, for those of you that aren't in a calc class or have taken a calc class, I don't want you to stress over this because this actually is a lot easier than what it seems. What you see on the board up here is a position versus time function. Now, what that does, that x of t equals t squared minus 8t plus 18, is the actual position function relative to time that's graphed above. It's the exact same example. I've just given you a position function that we can now work with. Now, what we will need to do is go through 2 steps. One, we're going to go through a process called the derivative, which for this is going to be very easy. And then, on the last step, we are going to do our substitution. So let's talk about how we're going to take the derivative. Okay? Now, this x of t equals t squared minus 8t plus 18. It is our position function. In physics, what will happen when we take the first derivative of that is we will get a velocity function relative to time. This is probably different than the notation for those of you in calc as to what you did. If you did like f of x and you have f prime of x and double priming, that's stuff that math might use for that notation. But for us, this is a position function where it would tell us our position at any given point in time. This function will tell us the velocity at any given point in time. So how do we do this? Well, we take a look at each term. What is the first term in this function? T squared. And for every single term, we will do the same thing. Step 1, we take our exponent, which is 2, and we multiply it by the coefficient. What is the coefficient of t squared? It's just 1. Can you do 2 times 1? I hope so. That gives you 2. So step 1 in each term is exponent times coefficient. Step 2, your exponent decreases by 1. It goes from t squared to t to the first. And do we express what t to the first is? We just leave that typically as t. Okay, so that's that term. We're done with the t squared. That has become 2t. Then we take a look at the next term, which is negative 8t. That's how we will treat it. But what is the exponent, Troy, in negative 8t? 1. What is 1 times negative 8? It will just be negative 8. But then instead of t to the first, that would become t to the 0. And anything to the 0 power is simply just the number 1. So that, instead of becoming t to the 0, it just becomes 1. 1 times negative 8 leaves us with negative 8. So then this plus 18, that would just drop off the end. I'm simplifying this, but that's all we would do for every term. Now, we have a velocity function. If we want to know the velocity at 1 second, we plug in 1 for every value of t and move on. If we want to know the velocity at 2 seconds, that same function, we plug 2 in for every value of time. If we want to know the velocity at 3.856 seconds, what would we do? We plug in 3.856 for every value of t, and we'd be able to find the velocity at that point. So let's do what we need to do. Let's find the velocity at a time of 2 seconds. Well, 2 multiplied by our time of 2 seconds minus 8. Our velocity at a time of 2 seconds. 2 times 2 is 4. 4 minus 8 is? Negative 4. And units, since it is a velocity, meters per second. Now, doesn't this match this? Yes, it's 2 different ways of doing the same thing. Now, I know we're not always going to be giving you a beautifully drawn tangent line, okay? But we can do this. And if this is the same problem, this is what's nice about it, we don't have to do that derivative over again. We've already found the velocity function, okay? 2t minus 8 is our velocity function. So now we can find our velocity at 6 seconds. Even though we never did actually calculate it based off the tangent line, we can figure out what it should have been. Okay, so 2 times 6 minus 8. 12 minus 8 would give you, okay, that would be 4 meters per second. So if we would have found the slope of that tangent line at that point, we should have got something close to 4. Does everyone see what we did? Okay, I want to do one more thing, and this isn't actually even in your notes. I'll just insert a thing after we do right here. Let's make up another function and go through the derivative process again. Okay, I'll have you guys help me build this. Pete, give me a number between 0 and 10.
5.
Okay, 5t to the third. Marissa, give me a number that's between 0 and 10. Minus 3t squared. Noah, give me a number that's between 0 and 10.
8.
Plus 8t plus 5,932. Why? Just because. All right. So if we, just to do the derivative process again, just so we understand what we're finding. V of t, let's look at this term. What do we end up getting? It would be 3 times 5, so that would be 15t squared. Does everyone see that? Then we look at our next term, negative 3t squared. That would become minus 6t. So it would be t to the first at that point. Then it would be plus 8. And that would drop off. We wouldn't have to worry about the 5,932. So then that would be our velocity function for what we started with. Does that make sense in process what we do? I know with everything that's new, it takes some time to get used to for those of us that haven't done derivatives before. But the nice thing is, once we have this, then we can literally, at any value of time, figure out what the velocity would be at that moment. And I know, for those that are in calc, to position functions and things get much more complex than that, absolutely. Okay? But that's where we're going to keep it in terms of what we're doing. So I give you the option on certain assignments. And when you get to your test, I will give you the option. You can either draw the tangent line and find the slope, or you can do the derivative. And I think, as almost all of you will find, doing the derivative is going to be a lot easier, and it's going to give us an exact value, so it's good on multiple. And so we'll kind of get some practice with that a little bit later. All right. Okay, so taking a little bit of a step in a different direction. Average speed. Okay, so we talked about average velocity and instantaneous velocity. Now average speed. Okay, I need you to fully understand that average speed is totally different than average velocity. They are in no way related to each other whatsoever. Why? Average velocity is based off of displacement. Average speed is based off of distance. Okay? And I know you say, well, they're really just the same thing. They aren't really. They are quite different from each other. But average speed is just simply going to be your total distance divided by total time. Unintelligent people use speed and velocity interchangeably. So you are intelligent people, and we will now know that there is a big difference between speed and velocity, a point that we're going to prove through a couple of other problems. So here we go. During the 2012 Summer Olympics, I guess maybe I can update it since it is the 2016 one to see if you've broken the other records. But during the 2012 Summer Olympics, Michael Phelps swam 4 50-meter laps in 1 minute and 51 seconds to win the men's 200-meter butterfly and set a new world record. This is not a trick question. What distance did he cover? He went 200 meters at the 200-meter race. But he did 4 laps in an Olympic pool. So started at one side, went down, came back, went down, came back. What was his displacement? 0 meters. Because again, if you remember our baseball example from last class, okay, we only care about the displacement where we start and where we finish. So, what was Michael Phelps' average velocity during this race? Well, since average velocity is displacement divided by time, his average velocity was 0. Congratulations, Michael Phelps. You just set a new world record. Your average velocity was 0. Do you think that would be important information for him? Probably not. What would be more important? Average speed probably would be much more important. Talking about the fact that he did 200 meters in 1 minute and 51 seconds. And we would have to convert that minute and 51 seconds, but that is going to be much more helpful information in terms of what we're looking to find. Okay, so give you a real life example. Must have been something about 2012. In June of 2012, my wife and I, we took a trip to Europe, and I am a big car nut. I love cars. It's just kind of neat. And one of the things that we did when we were on vacation, we were in Germany, is we went to a place called the Nürburgring. For those of you that like cars, and you may have heard about this place. It is a racetrack in Germany that is 13.1 miles long. And this is set in the Eifel Mountains. It is not your average NASCAR track either, in the sense that there are 131 turns in that 13.1 miles. And we had a professional race driver in a BMW M5 that took us around at great speed. And was actually weaving in and out of other people trying to drive their laps around the track too. Now, we completed 1 lap. We were just passengers on this ride, and we completed 1 lap, and I timed it. It was exactly 9.5 minutes. Now, would average velocity be something that would be important information here? No, because even though that's a 3-dimensional problem at that point, our final point and our starting point were one and the same. Would average speed be something that would be more helpful to describe the situation? Yes. And we're going to find the average speed, and we're also going to talk about a couple of other important things. Speed is just distance divided by time. But as with all things in physics, we must ensure that things are in the proper units before we do any substitution. So we have to convert two things. We must convert miles to meters and minutes to seconds. So let's talk our way through how we will do that. 13.1 miles. Much like you probably did in chemistry, we're going to use a unit conversion in order to get where we need to be. So we're going to multiply it by a ratio that is equal to 1 that will allow us to convert units. And if we're trying to convert from miles, the miles would need to be in the denominator because it would cancel out. What we are converting to in this case would be up top. And not that you know this at this point, but this is something you need to commit to memory. You will get 2 refreshers on this number today. This is your first. There are 1,609 meters in 1 mile. Again, that number is one you need to know. Because when we start to, as we will do later, convert from miles per hour to meters per second, since we use miles per hour to express everything in terms of our velocities and speeds here in the U.S., we need to be able to make those conversions very quickly. So this is not necessarily a complex calculation. The miles would cancel out, and it would leave us with this. So 13.1 times 1,609. When you carry that out, what do we get? Tyler, you got it? But he is finding it. I do appreciate that. 7.9, and that is in meters. For those of you that are quick on the uptake, what does that express in kilometers? 21,077. I'm sorry, 21 kilometers, 21.078 is around that, kilometers. Okay? That would be in kilometers. So that's in meters, which is good, which is the way we need it. We also need to deal with this 9.5 minutes thing. The 9.5 minutes, same thing, multiply it by a ratio that's equivalent to 1, that would cancel everything out, so minutes would have to be here, seconds here. How many seconds are there in 1 minute? 60 seconds. So 60 times 9.5 gives us 570 minutes. Oh, 570 seconds. Okay. That's better. I don't like expressing time. Now, at this point, does this become a very easy problem? Yes, it does. Okay? We have our distance in meters, so 21,077.9. No need to put units because it's in the SI units. Divided by 570 seconds. Pluggy chuggy, and we'll get our average speed. What do we get? 36.979. Good. Meters per second. That is our final answer, which would be our average speed for 1 lap around the Nordschleife. However, that number doesn't mean much to you at this point because we don't normally think of things in meters per second. That is an average speed of, I think, 82 miles per hour and change. Speedy. I will say that there were the slowest part of the track we slowed down to about 35 miles an hour, and the straight along the back stretch of it, we hit 155 miles an hour. Okay. So, a very fast lap around the Nürburgring. And I do have to commend the driver. There actually was a part where someone actually had a crash in the track, and he also had to slow down to about 30 miles an hour for a couple of seconds. They do have competing, right? Like car manufacturers go and test their cars there a lot, and they do have a contest of sorts that do lap records. But in terms of lap records, then you talk about the most extreme of performance cars, and there are some that are lapping it in, close to about 8 minutes. So, it is. And then I will say I'm a thrill seeker of sorts, and this was definitely one of the most unique experiences of my life. So, And I like cars. I've been around several other tracks before, and this was that was kind of pushing the limits a little bit, but also fun.
Do they have a top gear style wall?
No top gear style stuff. All right, instantaneous speed. Kind of march forward because we're almost through what we need to today. Got this and one other thing. Instantaneous speed is just like you'd imagine. It's the magnitude of your instantaneous velocity. So if you were driving 50 miles per hour east, isn't your speed just going to be 50 miles per hour at that moment? Yes. That works with instantaneous data. However, average speed and average velocity are two totally different things. Going back to the Nürburgring example, okay, our average speed was 82 miles per hour with that equate speed. Okay, and our average velocity was 0. Those are two totally different things because they're based off different values. So do not plan on trying to take the magnitude of average velocity. Like velocity and speed are calculated based on different things. Bless you. All right, one last concept. This is something that's new, but another term that we need, and that is acceleration. As we've seen, acceleration can change with time because the velocity of something is going to change over a period of time in certain examples. Okay? And in physics, we need to quantify changes in velocity just like we quantify changes in position. Okay? Now, when velocity changes with time, a particle is going to undergo acceleration. And you could read that in reverse order. Acceleration means any change in velocity. So if you speed up, do you experience an acceleration? Yes. If you slow down, do you experience an acceleration? Yes. Trick question to make you think. If you go at a constant speed in a circle, are you accelerating? You are at a constant speed in a circle. Bless you. Let me ask a precursor question. Are you changing your direction as you drive in a circle?
Yes.
So are you changing your velocity?
Yes.
But your velocity is speed in a given direction. So if you are talking about changing your direction, are you changing your velocity? Yes. So even though it's constant speed in a circle, you technically are accelerating. And that's a unique case. And we'll talk about that in January, but it is something I do need you to know. It is any change in velocity. And technically, and we will talk about that a little bit later, we can also find it on a velocity versus time graph. Okay? As with velocity, when motion is one-dimensional, okay, we can simply use a plus or a minus to indicate a direction for acceleration. And acceleration has units of meters per second squared. Why? Because we are taking velocity values in meters per second and we are dividing that by time in seconds. So meters per second divided by seconds leaves you with meters per second squared. Now, there is a way in which we will figure out whether accelerations are positive or negative. And I don't want you to think that positive acceleration means speeding up and negative acceleration means slowing down. That's not always the case. And we'll chat about what that is after we do 2 quick samples. All right, not in your notes, but important. It was what we just talked about. Top example, car is speeding up from 30 kilometers per hour to 60 kilometers per hour. Is there going to be an acceleration associated with that? Absolutely. It's increasing its rate of travel. The bottom example, where it's approaching a stop sign from 60 kilometers per hour, is it accelerating there? Absolutely, because we are changing our velocity. Middle example, constant speed going around a curve. Is it accelerating? Yes, because the velocity is changing with the direction component of that. All right. Sample problem A. Suppose a plane starts from rest. Anytime we hear something is at rest, we know that the velocity at that point is 2 6. Good job. Okay. Then the plane accelerates down the runway, and at a time of 29 seconds, it attains a velocity of 260 kilometers per hour, where the plus sign indicates it is traveling to the right. So we're going to determine the acceleration of the plane. There should already be a red flag that popped up in your head. Red flag. Something's off here before we proceed. We see the kilometers per hour. Okay? What does that have to be expressed in? Meters per second. So let's talk about the conversion from start to finish. Okay? 260 kilometers per hour. Let's do a simple unit analysis. Multiply that by a ratio. Let's start with the kilometers first. Where does kilometers need to be in order to convert this into meters? The numerator or denominator? Denominator. So kilometers are down here. We're going to convert it to meters. Not a trick question. In 1 kilometer, how many meters are there? There are 1,000. Good job. Then the kilometers would cancel out, but that would leave us with meters per hour. Close? Just not there. Then we need to convert our value of time. And since the hours are in the denominator here, where do the hours need to be in our final ratio? In the numerator. And then we would have seconds. So we need to figure out how many seconds there are in an hour. How many seconds are there in a minute? 60. How many minutes are there in an hour? 60. 60 times 60 is 3,600, correct? Yeah. So it would be 3,600. So what do we do to convert? Because that would take care of our hours. We take our value, which in this case is 260, multiply by 1,000, divide by 3,600. Everyone is doing this calculation right now. And if when you think you have a quality answer, let me know. Absolutely, 72.222 meters per second. Okay, so that is that value expressed in meters per second. Now we can do our acceleration calculation. I'm going to change things just slightly from what you've seen previously. Now, t by itself technically stands for a duration of time. And I know that you're given a t initial and a t final. The reality of it is we don't do it that frequently. Okay, we need to just go ahead and state that it is a duration of time of whatever we need. Okay? And now that we know what we need, this will be pretty easy. Open parenthesis, our final velocity, which is 72.222, minus our initial velocity, which was, you say, all divided by our duration of time from 0 to 29 seconds, it's just 29. Sluggy chuggy. And by the way, I may have stated this before, you may want to make sure that your lowercase letter t's have happy little feet on them, just so that we can differentiate t's from plus signs, because we will very soon have a lot of t's and plus signs in the same place. Marissa, what do we get? 2.490, and since it's acceleration, meters per second squared. Now, I will talk in a minute as to how we can check whether this should be a positive or a negative value. Okay? Right now, I just want us to be able to do that part of it. Any questions with sample A? No. We'll chat in a second. All right, do me a favor then. I would like for you on your own to do sample problem B. It should be a little bit more straightforward since there are no conversions. Careful. Remember that T stand for a duration of time. All right, Greta, what did you plug in for B final? Okay, put 13, let's see, 13 minus our initial velocity of 28. Okay, all divided by our duration of time of, we go from 9 to 12 seconds. What is the difference between 9 to 12? Okay, so that would be 3 seconds there. Okay, so we go ahead and we find that, and it actually should give us a nice round number. Ethan, what do we get? Okay, it is 13 minus 28 in our numerator. So should that be a negative value with how it should calculate? Okay, it should. Okay, so we should get that as a negative 5 meters per second squared. Now, I would like to make a general statement that is probably going to confuse you. And it's something that we're going to develop a lot over the next couple of classes. But I want to tell you, how do we figure out whether acceleration is positive or negative? You ready? It's easy to understand things when you talk about speed. When something speeds up, the displacement and acceleration are in the same direction. When something speeds up, the displacement and acceleration are in the same direction. Are you ready for this? If an object speeds up going to the right, what kind of acceleration should you have? Positive. If you want it, people aren't ready for it. If you speed up going to the left, what kind of acceleration do you get? Negative. So positive acceleration does not mean speeding up or slowing down. It depends on what's happening with your displacement and your acceleration. The converse of that statement is also true, meaning if you are slowing down, your displacement and acceleration will point in the opposite direction. You weren't confused before, hold on for you right now. The first statement is that if the object is speeding up, I mean it's getting faster, then the displacement and acceleration are in the same direction. If an object is slowing down, then the displacement and acceleration will be in opposite direction. So, if something is going to the right and slowing down, we're going to get a negative acceleration. This car technically is going to the right because the velocity values are positive. Okay? And it is slowing down. So it's okay that we get a negative acceleration. We should. Double negative examples that throws everyone for a loop. If something is going to the left and slowing down, it is a positive rate of acceleration. Okay? And I don't want you to feel like right now that you absolutely have to get that before you move on. Right now, if you do a good job of checking your numbers on the calculation side of things, it should kick out the correct positive and negative for our acceleration. One of the many things we're going to develop over the next couple of classes is our understanding of the positive and negative acceleration. We're going to do a lab next class. That part of that is going to help us to understand what's going on. Okay. In terms of our note packet, we're going to stop here for now, but I want to at least generally talk you through the two things that are due for next class. The first of which is the elevator of depth graph that you are going to complete. This is based off an episode of Mythbusters that we're not going to have the time to watch today, but what happens is they go ahead, take an elevator up, and they drop an elevator from a very specified height. Okay, several stories up. Okay? What we are going to do, even though it's vertical data, is we're going to graph this, and we're going to find the instantaneous velocity at 3 points. Now, if you can, bear with me for just a couple minutes. Just put your eyes on the board for a second. I need you to imagine this is the graph that you're going to have. It's a 4th quadrant graph because look at your position data. We start at the origin and it drops from there. It's going to give us negative position data. That's why we're in the 4th quadrant, which is why the x-axis is up here. So your labels and your units and everything are going to go up top because we're in the 4th quadrant. When you graph this, I'm going to tell you you're going to get an exponential curve. You will still connect your data points individually, straight edge ruler, individual points. But the overall trend is going to look something like this. Thank you. And what your task is going to be, once you get to that point, I'll drop my hands because it's still not going to turn out correct. To find the instantaneous velocity in 2, 10, and 15 seconds, you have to draw a hand-drawn tangent line. So you'll have to go through, I will tell you, your scaling should be correct. It's going to be, your first tangent line will look something like this. So at this point and one other point on that line, you'll have to find the slope of that tangent line. Then I'll draw them different colors just because, and I'm completely just eyeballing this. Okay, then maybe that might be your next tangent line. And at this point and some other point is where you find the slope of that tangent line. And then you'll have one more at 15 seconds. And again, I'm just completely, I didn't even come close to hitting the curve on that one. But let's assume that I did, because you'll do a better job than me. Then you'll use that point and one other one to find the slope of that tangent line. So A, this is just making a good position versus time graph again. But we're also going to have an exponential curve. You will hand draw your tangent lines and find the slope. Am I expecting everyone to get exact values for this? No. We all should be hovering right around a certain point if we make good quality graphs. And I'll be able to tell whether it's good or not, because it should be pretty close to whatever it is that we're doing. But we do need to be able to draw those tangents.
The lines in this are so confusing.
Okay. I know if you take a look at what you have, especially in the copied version, some of these fainter lines in between don't show up as best you can. You probably aren't going to be using those lines anyway. Because if we go ahead and we try to space it out as best we can, I would use what looks like the darker lines, and that's going to give you a better approximation of where we should be. Right? So don't just like, if you can't see the one line, don't skip it. Use the darkened lines as your grid practice. Okay? All right, that is this, and I'll have you do that in a second. Now, one more thing, I'm going to let you turn to your acceleration practice problems. The other assignment that is going to be due by next class. Okay? With your acceleration practice problem set, I want to let you know that you have several instances here where you will need to convert from miles per hour to meters per second. We did the miles to meters. We did that on the Nürburgring example that I gave you. And I did give you the friendly reminder at the top of this page that 1 mile is equal to 1,609 meters. The hours to seconds conversion, like we did the kilometers per hour, that part of it's still the same. Okay, so you would just be multiplying by 1609, dividing by 3600 in order to go from the miles per hour to meters per second. If you feel comfortable with it, which I still want you to practice it a couple times, you don't have to show me your conversions, but they have to be right. So I would suggest the first couple of times you do the miles per hour and kilometers per hour, because there's a mix that's in there, you might want to just do a couple of them just so we get used to, okay, this is what we do for this. Okay, but it's not going to be a requirement in terms of that assignment. Any questions with what's due for next class?